Okay, so, hold on. Okay. All right. So, the topic of chapter 11 is dealing with atomic structures or the structure of the atom. But before we get into the structure of the atom, we have to talk about the nature of electromagnetic radiation, right? And in order for us to understand the nature of electromagnetic radiation, we have to understand the nature, the different properties of a waveform, all right? So a wave is something that can be generated in different ways. One way that I'm quite sure you all can appreciate is if you take a rope, and I'm quite sure you probably did this as a kid. If you take a piece of rope and it's long enough, let's say I can attach it to the wall at the back of the classroom, and I pull down the end of it and I move it up and down, right? Eventually what will happen is that a wave will be generated along the length of the rope. So it may look something like, well, somebody just left a message. Let me see what this person is saying. Oh, somebody was asking if this is the last class. Oh, she, okay. Yeah, sad to say, Miss Jones. This will be the last class. Okay, so let me get my something in order here. So the waveform will look something like this. And please forgive my poor artistic skills. I'm not gifted in that here. But let's say this is a line which represents the initial position of the rope, and then you start moving the rope up and down. If you're holding it from this end, what you're going to end up with is a waveform which looks something like this. All right. And based on that, we can talk about several definitions associated with the different properties of a wave. Now, the first definition I want to talk about is what is called a wavelength. And the symbol for the wavelength is used to represent the wavelength is lambda, right? Looks like an upside down Y, right? So this is the international symbol of wavelength as far as science is concerned, right? And by definition, the wavelength is a distance between two successive peaks or two successive drops. So if you have a minimum down here, where is a trough, then basically the wavelength can be either the distance between two successive peaks or the distance between two successive troughs, right? That's wavelength. And the unit of wavelength, of course, is any unit of length, right? It could be meters, centimeters, whatever, all right? Another property of a wave is what is called a frequency, right? And in some textbooks, the symbol for frequency would be the letter F or the Greek letter nu, all right? And the frequency is basically the number of wavelengths that passes a particular point as the wave is moving per second, all right? Now, the units of frequency is going to be seconds to the -1, and there's a special name given to this unit. It's also called the Hertz unit, all right? So that's the unit of frequency, Hertz, which is the same thing as second to the -1. Wavelength, as I said before, can be expressed in pretty much any unit of length, depending, all right? Now, another property that we need to talk about with respect to waves is the speed. I'm just going to fix right here. The speed of a wave, right? And that will be equal to the wavelength times the frequency, all right? Now, usually, when you're using this formula, the wavelength will be expressed in meters, and the frequency, as I said before, will be expressed in seconds to the -1, which means that the units of speed will be meters second to the -1, which is the same thing as meters per second, all right? So this is the equation which basically ties the speed with the wavelength and the frequency. Now, in this chapter, we'll be talking about radiation, right? Electromagnetic radiation. And it turns out that all forms of radiation display properties of a waveform, all right? And there are different forms of radiation, including the type of radiation that our eyes are sensitive to, which would be the the different colors of light. In fact, let me get out of this here so I can show you what is called the electromagnetic spectrum. So let me open files. And let me go to lecture notes. And then chapter 11. Actually, I brought this up earlier so I can show you the rest. And let me, there it is here. All right, so the magnetic spectrum. Okay. So I talked about the wavelength, frequency, and the speed, right? And that's the relationship between them, right? So this is a spectrum right here. And basically, the electromagnetic spectrum is basically usually expressed as a chart, which shows you the different types of radiation, and they're ordered in this case according to increasing wavelength going from left to right. All right. Now, let me just say firstly that all forms of electromagnetic radiation have the same speed, right? Now remember I said that the speed of a wave is equal to lambda, the wavelength, times the frequency, which is nu, all right? Now, when it comes to electromagnetic radiation, they all have the same speed, which is 3.00 times 10 to the 8 meters per second. That is true for every form of electromagnetic radiation. And this is usually symbolized with the letter C, right? So C in this context is the speed of all forms of radiation, right? So for all these different forms of radiation, what you'll find is that the difference between them would be their wavelengths and therefore their frequency, because the wavelength times the frequency gives you the speed of the radiation, all right? So at the low end in terms of wavelength are the gamma rays, and then you have the X-rays, and then you have the ultraviolet rays, and then you have the visible region. Now the visible region is basically the different colors of light that our eyes are sensitive to, right? So we can detect with our eyes the different colors of light, which starts with violet, indigo, and blue, and it runs into green, and then yellow, and then orange, and then red. And there's a memory tool you can use to remember the order of the colors here. The way I remember it is ROYGBIV, red, orange, yellow, green, blue, indigo, violet, right, Biv. That's what I use to remember this order. All right. And I remember reading somewhere that among human beings, only the females can tell the difference between indigo and violet, which I'm tempted to believe because I can't tell the difference between indigo and violet. All right. So the order that I have it here is in order of increasing frequency, right? The order here is in increasing wavelength, right? And that's because, of course, there's an inverse relationship between the frequency and the wavelength, right? Because when they multiply, they get the same value, which is 3.00 times 10 to the 8 meters per second, all right? And then after the visible region, the red part of the visible region, then you have the infrared, then microwave, and then you have the radio waves, and so on, all right? So that's basically the electromagnetic spectrum. As I said before, our eyes can only determine or identify the visible region or detect the visible region. For the other forms of radiation, our eyes are not able to detect those, so we have to use instruments in order to detect those forms of radiation. Okay, so we get back over this here. So that leads us now to assignment number 11. So let me hand it over to you guys here. So that's for you. And that's for you. And for you guys out there in Zoom. I think I may have published it already. Let me see here.
You posted
Yeah,
it.
it's published.
Wait, no, okay, good. All right, so let me just get there. Assignment number 11. Yes, I did publish it. All right, so what I'm gonna do, because let me see here. Pretty much the first. Let me see. First, 14 questions are pretty much very simple and similar. All of them, from questions 1 through 14, require the use of the equation I just showed you, which is C is equal to frequency. C is equal to frequency multiplied by wavelength, all right? So the first question says, what is the frequency in hertz of a blue light having a wavelength of 425 nanometers, all right? So the question is asking for the frequency, which means that the frequency nu would be equal to C over lambda, right? Now we know C is always going to be this value, 3.00 times 10 to the 8 meters per second divided by the wavelength. What's the wavelength? 425 nanometers. However, we have nanometers here, we have meters here, so we have to convert one of those units into the other one. So I'm going to convert the nanometers into meters, and 1 nanometer would be the same as 10 to the minus 9 meters. So this cancels with that, this cancels with that, and we do the number crunching. Let me get my sheet calculator here. So 3 times 10 to the 8 divided by 425 times 10 to the minus 9. And according to my calculation, rounded off to 3 sig figs, the answer is going to be 7.06 times 10 to the 14. And the units here would be 1 over s, which is the same thing as s to the minus 1. Or you can say hertz, doesn't matter which one you use. They're both correct. And that's it. Any questions about this? Any questions?
Where did 10 to the ninth power come from?
I'm sorry?
Where did the 10 to the negative 9 come from?
Oh, so nano, right? The prefix nano is the same thing as 10 to the minus 9, right? So 1 nanometer will be equal to 10 to the minus 9 meters. There are 2 pages in the table that you'll have access to during your test, which gives you the meanings of the different prefixes, milli, micro, deca, nano, and so on. So you don't need to memorize it. You can just consult that table. Okay, any other questions? Any other questions? Okay, so if you understand number 1, you should be able to do number 2. Basically, it's the same thing. They gave you the length. In fact, it's even easier than number 2 because they gave you the length in meters. So you don't have to convert to meters because they gave you the length in meters and they're asking for the frequency. So it's the same equation you're going to use. You just plug the numbers in and get your frequency, which is what the question is asking. All right. So I'm going to leave that for you to do. Let me see what's next. Number 3, same thing. Let's see, number 4, same thing. Okay, so number 5 now is kind of different because it's asking for the wavelength, right? So again, the equation is C is equal to lambda times nu, but this time the question is asking for the wavelength. So lambda will be equal to C over nu, right? So they gave you, well, we know what C is already, 3.00 times 10 to the 8 meters per second divided by 3.76 times 10 to the minus 4, I'm sorry, 14, not minus 14. It should be 14 seconds to the minus 1. And that's it. So 3 times 10 to the 8 divided by 3.76 times 10 to the 14. And according to my calculation, I got rounded out to 366, 7.98 times 10 to the minus 7 meters, because this will go with that, and that's it. All right? Any questions about this one? Any questions? Any questions out there in Zoom?
On the numerator, is that MLS at the very end?
Oh, no, that's M/S. Let me fix that up. You're talking about this, right?
Yes, sir.
Okay, so that should be M/S, meters per second.
Okay. Thank you.
So that's that for number 5. And let me see here, number 6, very similar to what we did earlier, so I'm going to skip that. Number 7. Number 7 is very similar to number 5. Right? Same setup here. The only difference is that the frequency is 2.99 hertz. And let me see here, number 8, same thing. Right? Scroll down here. Number 9. Same as before. They gave you the wavelength and they're asking for the frequency. Same thing for number 10. For number 11, just like we did before, they're asking for the wavelength. And let me see here, number 12. Okay, now one thing I want to mention here about number 12. And I think this is also in the table that I have posted. I'm not sure, but since I'm not sure, let me talk about this. In the case of number 12, there's a unit here that you may not have seen before, which is called the angstrom, right? So basically 1 angstrom, it's not a metric unit, by the way, right? But it's a unit that is used by scientists. 1 angstrom is the same thing as 10 to the minus 10 meters, all right? So you have to keep that in mind when you're doing this calculation. So in this case, somebody just said something. Somebody just said something. Oh, okay, somebody was asking about what chapter we're on, all right. And somebody did answer, okay. So going back to this now, so in this particular case, let me do this one for you. So they're asking for the frequency. The frequency would be the speed, which is 3.00 times 10 to the 8 meters per second, divided by the wavelength, which is 2110 angstrom, and then we'd have to multiply this by 1 angstrom down here and 10 to the minus 10 meters above, and that's it. So 3 times 10 to the 8 divided by 2110 times 10 to the minus 10. And according to my calculation, this works out to be equal to 1.42 times 10 to the 15. And the units here would be seconds to the minus 1 or hertz, because this will cancel out with that, this will cancel out with that. So you'll be left with seconds to the minus 1 or hertz as your final unit. Yes, sir.
So is the speed always 3.00?
It doesn't change, exactly. That's true for all forms of electromagnetic radiation, right? That's true for the different colors of light. That's true for infrared, true for ultraviolet, microwave, whatever. So that's one constant. So therefore, for that reason, because C is equal to nu times lambda, right? You have an inverse relationship between frequency and wavelength, right? So the higher the wavelength or the longer the wavelength, the lower be the frequency and vice versa. Because when they multiply, they give the same 3.00 times 10 to the 8 percent. All right. Okay, so if there are no questions on that, let me clear this and scroll down. Okay, same thing, you should be able to do this one based on what we did earlier in number 12. And the same thing in 14, you should be able to do that one based on previous questions. Okay, so I'm going to leave the rest of those for you to do, because I want to get to the other part of this chapter, which deals with the electron configuration, right? So basically, and there, of course, if you watch the videos, you have been informed about how we get from waveform of radiation to the atomic structure, which I won't get into right now. But basically, one of the more important discoveries of the atom is how the electrons are arranged, right? And it turns out that basically the electrons are arranged in shells, right? And within these shells, we have what are known as orbitals. And orbitals are basically regions in an atom where there is the high likelihood or probability of finding an electron. And you should have learned that different orbitals have different shells. In fact, let me go to the PowerPoint here. So, of course, there was a discussion of the Bohr atom. Didn't spend too much time talking about that in the videos. But basically, the Bohr atom is used to explain the different forms of radiation that the atom will emit as a result of electrons transitioning from one orbit to the other. And then we talked about orbitals as a result of wave mechanics. And as I said before, here's a definition of an orbital. It's a region in space around the nucleus where there's a high probability of finding an electron. So you have different energy levels, which are called shells. And within these shells, you have the orbitals, as I said before. So the shells basically have a certain amount of energy associated with them, and they're designated with an n number, which is called a quantum number, n equal 1, 2, 3, 4, all the way up. And you'll notice that as you go up in energy with respect to the shells, the energy gap between the shells becomes smaller and smaller, right? So the energy gap between n equal 2 and n equal 1 is that big. And then between n equal 3 and n equal 2, it's smaller. And between n equal 4 and n equal 3, that's even smaller. And that trend continues, right? Until to infinity, where basically all the shells merge. So within each shell is where we have what we call the orbitals, right? And this, I think, explains pretty well the arrangement as far as the orbitals within the shells are concerned. Now, within each shell, you have what are known as subshells, right? Now, in the case of the first shell, there's only one subshell, and that is designated 1s. In the case of the n equal 2 subshell, in the case of the n equal 2 shell, there are two subshells, 2s and 2p. And then in the case of the n equal 3 shell, you have three subshells, 3s, 3p, and 3d. And then in the n equal 4 subshell, you have n equal 4 shell, you have four subshells, 4s, 4p, 4d, and 4f. And it continues, but I won't go into the higher shells and their sublevels, all right? So this is just summarizing the shapes of the different orbitals within the subshells. In the s subshell, you have what are known as s orbitals, and they are spherically shaped like a ball, as you can see here, right? And then we have the fact that an orbital, and that is true not only for s orbitals, but for any orbital, the maximum capacity in terms of the number of electrons they can accommodate is 2, right? So in the s orbital here, you must have 2 electrons maximum, and if you do have 2 electrons maximum, they will be spinning in opposite directions, all right? So there's a rule which, for those of you who plan to do Chem 1, it's called the Pauli's exclusion principle, which basically says that if you have 2 electrons occupying the same orbital, they must be spinning in opposite directions. And there are reasons for that, which I won't go into right now. It's a bit above our level right here. So that's basically what happens in the case of the s subshell. Now, in the case of the p subshells, the number of p orbitals that are present will be 3. And this is what they look like. They are oftentimes described as dumbbell shaped, and they are aligned at mutual right angles. So if you're familiar with the Cartesian system in math, you have the x, the y, and the z axis, right? So you have one p orbital that is aligned along the x-axis, that is called the px orbital. You have one that is aligned along the y-axis, that's called the py orbital, and then you have the pz orbital, which is aligned along the z-axis, right? So this is what they look like separately. I think I have a diagram here, or I should have a diagram here, which shows you what they look like together, right? So this is what they actually look like together, right? And they, as stated here, share a common center, all right? So in the p sublevel, where they exist, you always have a set of 3 p orbitals, all right? And then you have the d orbitals, which are these right here. Now, I won't expect you to memorize these shapes, but you do need to know that they exist, and you do need to know that within the d sublevel, there are 5 d orbitals present, right? And this is basically what they look like, all right? And then for the f sublevel, jump this here. For the f sublevel, there are 7 of them. I won't even show you what they look like. It's even more complex. But you do need to know that within the 4f sublevel, there are 7 f orbitals. All right. So just to summarize here, in the case of the 1s sublevel, you have a 1s orbital. In the case of the 2s sublevel, you have again an s orbital, which is a 2s orbital. Within the 2p sublevel, you have 3 2p orbitals, and then it continues on the way up. For the 3s sublevel, there's only 1 of them. In the 3p sublevel, there's 3 of them. In the 3d sublevel, there's 5 of them, right? And then when you get to the 4th shell, 1 s orbital, 3 4p orbitals, 5 4d orbitals, and 7 4f orbitals, which are not even shown here, right? But you do need to know that there are 7 of them, all right? So this basically summarizes the different subshells and the number of orbitals within those subshells for the different shells, right? So for the first shell, there's only 1 orbital, 1 sublevel and 1 orbital, that's 1s orbital. In the case of the second subshell, you have 2 subshells, 2s and 3 2p's. In the case of the third shell, you have 3s, 1 of them, 3 3p orbitals in the 3p subshells, and 5 3d orbitals in the 3d subshell. And then finally, at this level anyway, for the n equal 4 shell, you have the 4s, 1 of them, you have the 4p's, 3 of them, you have the 5 4d orbitals within the 4d subshells, and you have the 7 4f orbitals, right? So that's basically how the orbitals are distributed within the atom among the shells as subshells. And you need to remember as well, as I said before, that each orbital can have a maximum of 2 electrons, right? So for example, in the case, let me just choose arbitrarily, in the case of the n equal 2 shell, this 2s orbital will have 2 electrons maximum, and then each of these 2p orbitals can accommodate 2 electrons maximum. So the total maximum number of electrons that can go into the n equal 2 shell would be 8, right? 2 here in this 2s sublevel, and 6 here in the 2p sublevel, all right? Okay, so one challenge that is oftentimes encountered when we try to establish how the electrons are distributed is what would be the exact order of the electrons within the subshells. Now, that distribution that I just referred to, the way the electrons are ordered, we call that the electron configuration. And there are a couple of ways of representing that. This way that I'm about to show you is oftentimes referred to in some textbooks as the SPDF notation, right? So basically, in the SPDF notation, we use this symbolism right here, where this number represents the shell that we're concerned with, and then the P here represents the subshell, and then the number here, which is written as a superscript, represents the number of electrons within that subshell, right? So using this symbolism, we can determine how the electrons are distributed. Now, I want to go through this rather quickly. So let's start off with the simplest atom, which of course is hydrogen, has only 1 electron. So basically, where that electron would go, it will go into the lowest orbital of lowest energy, which would be the 1s orbital. So therefore, that electron will go here, right? So that's in the case of the hydrogen atom. The next element would be helium. Oh, by the way, so in terms of the SPDF notation, before I get to helium, the way we would represent the electron configuration of hydrogen is what you see here, 1s1. 1 represents the shell, S represents the subshell within that shell, and this one here represents the number of electrons within that subshell, all right? So the next element is helium, which has 2 electrons. Now remember, if 2 electrons are occupying the same orbital, they must be spinning in opposite direction, right? So therefore, that would represent how the electrons are distributed in the 1s subshell of helium. and we can represent it this way, 1s2, all right? The next element in line is lithium. So in the case of lithium, you have the 2 electrons going into the 1s subshell, and then you have this electron, this orbital here, or this subshell here, which will gain the 3rd electron, right? And therefore, this is it as far as how the electrons are distributed, and we can represent it using this symbolism right here, 1s2, 2s1, all right? And then you can continue to the next element, which is beryllium. So to get from lithium to beryllium, all we have to do is add an electron here. And again, the electrons must be spinning in the opposite direction with their share of the same orbital. So therefore, the electron configuration of beryllium is this right here, 1s2, 2s2. And then we get to the next element, which is boron, right? So boron has an atomic number of 5, which means that you have 5 electrons. The first 4 will go into the 1s and 2s sublevel, which means that the 5th electron can occupy any of the next available sublevel, any of the next 3 2p orbitals. So we're just going to put that 1 electron there, and therefore that would be it as far as how the electrons are distributed. And this would be the representation using the SPDF notation, 1s2, 2s2, 2p1. And then if you add another electron, that electron for the next element, which is carbon, right? So basically to get from board the carbon, not only do we have this electron here, but we have to add another electron. Now at this stage, what would happen is that the next electron would prefer to go into any one of the 2 vacant 2p orbitals, as opposed to joining this electron right here. And the reason why is because the electrons are negatively charged, like charges tend to repel. So therefore, instead of going into this orbital here, the next electron would go into any one of these 2. So therefore, this would be the distribution of the electrons in the case of carbon. And therefore, the electron configuration would be 1s2, 2s2, 2p2. And you can continue from here to the next element, which is nitrogen, where the next electron will go into the next vacant orbital, and therefore this will be the electron configuration of nitrogen, right? And then now to get to the next element, which is oxygen, right? To get from nitrogen to oxygen, we have to add an electron, and that electron can be added to any one of these 2p orbitals. So we get that, and therefore the electronic configuration of oxygen is, as you see there, 1s2, 2s2, 2p4. And then the next element, which is chlorine, basically, you're just going to add, so this was oxygen right here, you're going to add an electron to any one of these 2, and you're going to get this electronic configuration, which is 1s2, 2s2, 2p5, all right? And then the next element is neon, right? Which means that this was oxygen, and then you add 1 electron here, and that is neon, and therefore this will be the electronic configuration of neon, all right? And the next element will be sodium. So in the case of sodium, we have this already for neon. To get from neon to sodium, we add an electron. That electron cannot go into any one of these, so it will go into the next higher orbital, which would be the 3s orbital, and therefore this will be the electronic configuration of sodium, right? And then when we get to the next element, which is magnesium, what's going to happen? The next electron will be added right here to get this, and therefore you're going to end up with this electronic configuration of magnesium. And you just continue adding electrons to the next orbital, then continue following the rules in terms of spreading the electrons out among orbitals of same energy levels before pairing them up, all right? So let me just skip all this here. So this is what we just did look at a while ago. This is just basically a summary of how the orbitals are filled as you go from one atom to the next. Now, and then this is for the same process going from sodium to argon. Now, one of the issues that arises, especially when it comes to heavy atoms, is the order of the orbitals in terms of energy. Because you need to know that in order to determine the electron configuration, right? Just skip all this here. And what I really want to get to is a chart. Oh, before we get to that, this is very important. All right. As you can imagine, when it comes to the heavier atoms, like for example, tin, which has 50 electrons, or bismuth, which has 83 electrons, as you can imagine, when you're writing down the electronic configuration for those larger atoms, you have a huge or a long line of symbols, letters and so on, which in some cases is not necessary for, what you're trying to do. So what has been developed is a method of writing down an abbreviated version of your electronic configuration. So to illustrate this, how this happens is that, let's say we start off with the electronic configuration of boron, which is this right here, right? To get the abbreviated version, right? What was decided by IUPAC is that we look at the electronic configuration of the element in group 8 that precedes the element that you're concerned with. So, for example, in the case of boron, if you go to the periodic table, the group 8 element that comes before boron is helium, right? Helium has an electronic configuration of 1s2, right? So basically, to get the abbreviated version, we replace this part, the 1s2 here, with the symbol of helium in square parentheses, and then you write down what is left, right? And that would represent the abbreviated version. Now, this is not much of an abbreviated version when you compare these two, but if you go to a larger atom like sodium, right? This is the electronic configuration of sodium, right? Which element comes before sodium in the periodic table? Neon, right? That's group 8 element that comes before sodium in the periodic table. The electronic configuration of neon is right here, all right? So what do we do in order to get the abbreviated version? We replace all of this with the symbol of neon in square parentheses, and then you write down what is left beside it, which is 3s1, right? So when you compare these two, you can see that this here is more abbreviated compared to this. And I think I have another example here. Chlorine, okay. So in the case of chlorine, this is the electronic configuration of chlorine, right? What group 8 element comes before chlorine? Neon again, right? And neon has the electronic configuration of this part right here. So to get the abbreviated version of chlorine, we replace all of that with the symbol for neon in square parentheses, and then 3s2, 3p5, all right? And that's basically how you get the abbreviated versions. Okay. Okay, so here is where I want to get to this chart. Right. So when it comes to higher atoms or heavier atoms, it becomes more difficult for you to directly determine what the order of the orbitals are in energy. So this chart here is very useful for helping you to predict the order, right? And I remember as a student, what I used to do is, to remember this, is that I take a sheet of paper and I would write down 1s, 2s, 3s, all the way down to 7s in one line like that. And then for the second shell, I start with 2p, 3p, all the way down to 7p. And then at the third shell, 3d, 4d, 5d, all the way down to 7d. And then at the fourth shell, I start with 4f, 5f, all the way down, right? And then I draw the arrows as you can see here, right? And now based on that, you can determine the order of the orbitals in terms of the energy. All you have to do is follow the arrows from tail to head, right? So basically the order would be 1s. Remember now, you're following the arrows from tail to head. So 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then starting here, 3d, and so on and so forth, right? So that's basically how you obtain the order of the orbitals in terms of their energies. And based on that, you can determine the electron configuration of pretty much all the atoms that exist in the periodic table. There are some exceptions, which at this level I won't get into, all right? But pretty much this is what you use to determine the order, and therefore you can determine the electron configuration. So for example, let's see here. So for example, let's say, where can I squeeze this? Let's say you're asked to determine the electronic configuration of titanium, right? So the first thing I would do is look for the atomic number of titanium. It is 22. Now, you need to remember a couple of things. You need to remember not only the order, or you don't need to remember the order because you can get it based on the chart here, but you do need to remember the maximum capacity of each sublevel, right? For the S sublevel, it's 2. For the P sublevel, it's 6. For the D sublevel, it's 10, because the D sublevel have 5 orbitals. Each orbitals can have 2 electrons, so that's 10. And in the case of the F sublevel, there are 7 orbitals within each s sublevel, so the maximum capacity is 14, all right? As far as the s sublevel is concerned. So, in the case of titanium, we have 22 electrons per side. So the first sublevel is 1s, as we said here, so that's 2. First 2 electrons will go into the 1s sublevel, that's the maximum that can go into the 1s sublevel. And then for the 2s sublevel, that's 2 again. And then for the 2p sublevel, that maximum is 6. And then for the 3s sublevel, that's 2. For the 3p sublevel, that's 6. For the 4s sublevel, that's 2. So far, we have assigned 20 electrons, right? We have 2 more left over, so those 2 will go into the 2 sublevel and into the 3D sublevel, I'm sorry, and that's it. And therefore, this would be the full electronic configuration of titanium, all right? Now, if you are asked for the abbreviated version, then, as I said before, what you do is look for the group 8 element that comes before titanium. And that group 8 element would be argon. Argon would be all of this right here. All right. So therefore, for the abbreviated version, it would be this: AR in square parentheses, followed by 4s2, and then 3d2. And that would be the abbreviated version of the electron configuration of argon. Okay, so based on what we have just covered, you should now be able to do, let me get over this here. Part B, all right? So remember now, you may want to, unfortunately, I don't have a split screen thingy, or maybe I can, hold on, see. Maybe I can minimize this a bit, or because we need this chart. All right, let me see. Okay. I guess we can you all see that? All right. Okay. So let's start off with sodium. So the first thing I will do, no, the question is asking for the unabbreviated or the full electron configuration, right? Starting with sodium. First thing I'll do is look for the atomic number of sodium, which is 11, right? So we have 11 electrons to play with. So based on the chart here, the first sublevel will be 1s, which will have 2 electrons, then 2s, which will have 2 electrons, and then 2p, which will have 6 electrons. So we have used up 10 of the 11, which means that the 11th electron will go into the 3s sublevel, right? And that would be the full electronic configuration of chlorine, not chlorine, sodium. All right? And that's it. Okay, I think we did chlorine already, but let's do it again for the sake of practice. So in the case of chlorine, again, the atomic number is 17, right? So the first electrons will go into the 1s sublevel, then 2s2, then 2p6, and 3s2, right? So that's how many electrons so far? That's 12. And then we have the 3p sublevel. So that means that the remaining 5 electrons, because the 3p can have a maximum of 6, I'm sorry. So the 5 electrons will occupy the 3p sublevel, and that's it. So that would be the electronic configuration of chlorine. Okay, so let me see if you can do magnesium. What's the first thing you look for? In the case of magnesium.
The atomic weight.
The atomic number, not weight. So what's the atomic number of magnesium? 12, all right? Okay, so that means what? 1s would have how many electrons? 2s would have how many electrons? 2p will have how many electrons? And then 3s would have how many electrons? 2, and that's it. All right? Okay, nitrogen. What's the atomic number of nitrogen? 7, right? So it will be what? 10. 1s2, oops. 1s2, then 2s2, 2p3, exactly. And then silicon. What's the atomic number of silicon? 16. All right. So tell me what to write down. Hmm?
14, so, that's so.
14, you're right, I'm sorry. Yeah, so. Tell me what to write on.
1s2,
1s2,
2s2,
2s2,
2p6,
2p6,
3s2,
3s2,
3p2.
3p2, exactly. All right, very good. All right, so that's the first part. Now, the second part is asking for the abbreviated electron configuration. Now, what I would do if I were you is write down the full configuration first, and then based on that, figure out what the abbreviated is, right? So in the case of aluminum, the atomic number of aluminum is 13. It's 13. So it will be 1s2, 2s2, 2p6, 3s1, 3p2. All right? Make sure I did that right. It should be 2p6, I'm sorry. Okay, so that's it. All right. Now, as I said before, to get to the abbreviated version, we look for the group 8 element that comes before, in this case, aluminum. And that abbreviated, that group 8 element will be neon, and neon will have this configuration right here, right? So therefore, the abbreviated version would be this, followed by 3s1, 3p2. And that's it. Right? Any questions about this? Any questions?
It'd be 3s2 and 3p1.
I'm sorry, yeah, you're right. 3s2, 3p1. Thank you. Okay. Okay, in the case of carbon, carbon has an atomic number of 6. That's 1s2, 2s2, 2p2. Right? So what would be the abbreviated version? Well, let me ask you this first. What would be the group 8 element that comes before carbon? Helium. What's the electronic configuration of helium? 1s2. So therefore, you're going to put the configuration of helium here, and then you're going to follow that up with 2s2, 2p2. All right? Okay, the next one is fluorine. Fluorine has an atomic number of 9. Right? So the full electronic configuration is 1s2, 2s2, 2p5. So what do you think the abbreviated configuration is?
Helium, so it's 2.
Exactly. Okay. And then in the case of phosphorus, what's the atomic number of phosphorus? 15. All right. So in the case of phosphorus, 1s2, 2s2, 2p6, and then you have 3s2 and 3p3. Okay, so that's the full electronic configuration. What is the group 8 element that comes before phosphorus? Neon, and the electronic configuration of neon is right here. So we're going to put neon symbol in square parentheses, then 3s2, 3p3, right? And then boron, what's the atomic number of boron? 5. So 1s2, 2s2, 2p1, which means that the abbreviated electron configuration is helium in square parentheses, and then 2s2, 2p1. That's how that is done. All right.
Why did you choose neon? Because I heard you explain it, but for some reason it just went through my head.
Oh, because neon is the group 8 element that comes before phosphorus in the periodic table. So basically, once we identify that element, then we identify the part of the electronic configuration of phosphorus, which is the same as the electronic configuration of neon, which is this part right here. So we replace that with the symbol of neon in square parentheses, and then we put the rest 3s2, 3p3.
Okay, thank
All
you.
right. Okay, let's see here. What comes next? Let me clear this first. Okay, so I'm gonna leave part C for you to do. Basically, it's the same thing as in the case of part B, all right? Let me see what's next. And then in the case of part D, it's talking about completing this table. Now, let me just say that when it comes to the representative element, meaning the elements in groups 1A through to 8A, what you'll find, well, with the exception of the halogen, which is group 8A, right? What you'll find is that these atoms will tend to lose or gain electrons to form ions, and the number of electrons lost or gained will result in them ending up with the same electronic configuration as the nearest group 8 element. So an example of this is shown here, right? In the case of oxygen, right, the atomic number is 8. In terms of the number of electrons present within each shell, you have 2 in the first shell, 6 in the second shell, and then this is the full electron configuration, right? So the question here, or this part of the column is asking the number of electrons that are probably lost or gained. And in this case here, that would be 2, because when oxygen gains 2 electrons, you now end up with a full outer shell, which would be 8, which is usually an octet, right? So therefore, the number of electrons that is left after gain or loss would be 10, because you have 2 plus 8 giving you 10 electrons total. And the resulting charge on the ion is going to be -2, because before the charge is 0, when it gains 2 electrons, then the resulting charge is -2. So applying that same idea to sodium, let me see here. So in the case of sodium, sodium has an atomic number of 11, right? And in terms of the how the electrons are distributed among the shells, it would be 2 in the first shell, 8 in the second shell, and then 1 in the third shell. In terms of the full electronic configuration, that would be 1s2, 2s2, 2p6, and then 3s1, all right? And then now, in this case, sodium is a metal. It will tend to lose electrons rather than gain electrons. So therefore, in this case, it will gain, or it will lose this 1 electron, or lose this 1 electron, so that it ends up with a noble gas configuration. So you're going to put here lose 1 electron. And after losing that 1 electron, the number of electrons remaining would be 10. And in terms of the charge on the ion, when the atom loses 1 electron, it will gain a +1 charge. And therefore, that's how that is completed. All right. And let me just do this one again, just to help you out. Now, sulfur has an atomic number of 16, right? So in this case, the way the electrons will be distributed will be 2, 6, and I'm sorry, 2, 8, and then 6. I'm sorry, 2, 8, 6. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p4. All right. So in this column, you're going to put that it's going to gain 2 electrons, because when it gains 2 electrons, it's going to end up with the nearest group 8 element configuration, which is argon. And when it gains 2 electrons, the resulting electron count will be 18. And in terms of the charge, it's going to be -2. Right? And that's basically how you're going to do the rest of that table. So I'm going to leave that for you to complete.
Why did you say it would gain 2? Do you like
Because it will gain 2 in order to get the same electron configuration as the nearest group 8 element, which is argon. Right? So argon will have the electronic configuration where the 3p sublevel will have 6 electrons. So therefore, it's going to gain 2. Right? 4 plus 2 gives you 6. And therefore, it's going to gain 2 electrons as a result.
Okay, so you round down for 3, end up for 4, basically.
I'm sorry?
So 4, 5, never mind. I figured it out. Thank you.
Sure. All right. Okay, so that's basically how you're going to complete that table. All right, let me see here. Oh, okay, now this here, which deals with periodic trends. Not sure if I'll have enough time to. See here. Okay, me try to do this as quickly as I can. Okay, now there's certain periodic trends that you'll observe in the periodic table as you go from left to right of any period or top to bottom of any group, right? So basically, let's deal with going from top to bottom. That's easier to explain. As you go from top to bottom of any group, what will happen is that in terms of the atomic size, is that the distance between the valence electrons and the nucleus will increase. All right. So therefore, the size of the atom is going to increase as you go from top to bottom of any group. All right. Now going from left to right of any period, what you'll find is that as you go from one atom to the next, you're adding an electron to the valence shell, but at the same time, you're adding a proton to the nucleus, right? So the result of that would be that as you go, let's say we're taking period 2. As you go from lithium to beryllium, right? You're adding a proton to the nucleus, you're adding an electron to the outer shell, and what will happen is that the proton will draw the surrounding electrons closer to the nucleus, so the atomic size will decrease. And that trend will continue as you go across the period, right? So basically going from left to right of any period, what you'll find is that the atomic size will decrease, right? So that's important for you to understand in order to answer part E, number 1, which says, rank the following elements by increasing atomic radius, and it gives you carbon, aluminum, oxygen, and potassium. So you have to look at their relative positions in the periodic table. So let's see. Carbon is in period 2. Aluminum is in group in period 2 as well. No, actually period 3. Right? So I know that aluminum will be larger than carbon. Let me see where oxygen is. Okay, so oxygen is to the right of carbon, and then potassium is, okay, so potassium is in period 4. So basically, I can say straight off the bat, because carbon and oxygen are in the same period, and because oxygen is to the right of carbon, I can say that oxygen would be smaller than carbon in size. Now, please note that the question says you're ranking them by increasing atomic radius, right? So in other words, you're starting from the smallest to the largest, right? So based on the fact that oxygen is to the right of carbon in the periodic table, oxygen would be smaller compared to carbon, right? So the next question I have to ask myself is, what about the other elements? As far as aluminum is concerned, aluminum is in period 3, which is below period 2. So I'm going to say that aluminum would be larger in size compared to the carbon. And then potassium, which is in period 4, it'll be larger in size compared to aluminum. So this will be the final answer. Oxygen will be the smallest, followed by carbon, followed by aluminum, followed by potassium. All right. Okay. Then we have this thing about electronegativity. So let me quickly define what electronegativity is. Electronegativity is basically the ability of an atom to attract shared electrons to itself. All right. So if you have 2 atoms connected to each other by a bond, shared electrons, then the atom that has a stronger attraction for the shared electrons would be the more electronegative atom, right? And what you'll find is that electronegativity decreases going down a group and increases going from left to right of a period, all right? So with that said, let's see if we can answer this question. This question says, you're going to rank the following elements in order of increasing electronegativity, right? So you're going to start from the lowest electronegativity atom to the greatest one. So neon is a neutral, well not neutral, it's inert. So therefore it will have pretty much no electronegativity because it's in group 8A, right? The next in line, I would say, would be aluminum. All right. And then the next in line would be sulfur, because sulfur is below oxygen, right? And then oxygen, of course, would be the one with the highest electronegativity. So that would be the answer for number 2. All right. Okay. Any questions? Any question about this? Okay, let me clear this here. And scroll down. Okay, what's the difference between electronegativity and ionization energy? Okay, so electronegativity I mentioned before. It is the ability of an atom to attract shared electrons to itself. The ionization energy, maybe I should write this down. So the ionization energy is the energy required to remove an electron from a gaseous atom. All right. And it turns out that the ionization energy is dependent on the position of the element in the periodic table, right? If you remember when I mentioned the atomic size, how it varies, right? You should remember I said that as you go down any group, the distance between the valence electron and the nucleus increases. So what that means is that it becomes more easier to remove the valence electron. So therefore the ionization energy will increase as you go down a group. And then going across a period, what you'll find is that generally speaking, the ionization energy will increase because the atomic size becomes smaller. As you go across any period from left to right, the distance between the nucleus and the surrounding electrons will decrease, and therefore it becomes more difficult to remove the valence electron because of the strong attraction. And as a result, the ionization energy increases as you go from left to right of any period. So that's important to understand in order to answer question number 4, because question number 4 says, why does fluorine have a higher ionization energy than iodine? So all you have to do is consult the periodic table and you look at the positions of fluorine and iodine, and you see that they both occupy the same group, but fluorine is higher compared to iodine. So therefore, what that tells you is that the distance between the valence electron and the nucleus in the fluorine atom is shorter compared to the same in chlorine, right? Or in iodine, I'm sorry. So therefore, the nucleus will have a stronger hold on the valence electron, and therefore it becomes more, in the case of fluorine, it is more difficult to remove the valence electron compared to doing the same thing for the iodine, right? So the answer in the case of number 4 is that fluorine is a smaller atom compared to chlorine, compared to iodine, right? Fluorine is a smaller atom compared to iodine, and therefore the electron to be removed would be harder to separate from that atom because it's closer to the nucleus. And therefore, that's why fluorine has a higher ionization energy compared to iodine. All right? Okay. Is there anything else I need to say about this? Oh, okay. So let me clear this here. See what this question is asking for. Oh, why do elements in the same family, and when they say family, it means the same group, right? Have similar properties, right? And I remember I asked a similar question that I tested a student who said genetics. Anyway, the reason is they have the same number of valence electrons, right? Atoms in the same group have the same number of valence electrons. And that determines basically the chemical properties of those elements, right? So if you look at, for example, group 1, they all have 1 electron in their valence shell, right? And that fact caused them to behave chemically very similar, right? They tend to react the same way with other reagents and so on, right? So that's the answer for number 5, all right? And I think that's it for this particular section, all right? So what I'm going to do now is set up a job box for that one. So let me move here. Let me go here. So this is assignment number 11. And now, unfortunately, we didn't get to assignment to chapter 12, but what I'm going to do is I'm going to allow you to, I think I've already published the videos. Well, let me take care of this first. So, okay, so I'm going to open up a Dropbox for the due date of December 4th. Okay, and then what I'm going to do is I'm going to, if I'm not done so already, I'm going to publish the assignment number 12. And I think I've published the videos. Oh, it's published already. Okay. Let me just check the videos if that video is published already. I think I published it as well. Well. Okay, so it's published, right? Now, I'm going to give you the option of doing assignment number 12. Make sure you watch the videos. If you're going to do it, make sure you watch the videos. I think you should be able to, after watching the videos, you should be able to do assignment number 12. If you have any questions about that, please let me know, all right? And before you leave, let me just remind you that your final exam, I think I posted an announcement about that, but I want to make sure I tell the person. So for this class, the final exam will be Tuesday, December 9th, which is next week Tuesday, all right? Same time, same place. And it will be 2 hours long, and it's going to be comprehensive, all right? So I would suggest that you basically review, all the assignments, all the tests, and any past tests or whatever that I posted. In fact, before I forget, let me see if I can post a past final exam. Let me go here. Let me see if it's here. Okay, final exam. Oh, it's already posted. So let me just do a quick look at this here. Okay, so okay, so just by what I've seen so far, I would strongly recommend that you review this as well, just to get a feel for what the final is going to be like. So if you understand all of this here, you should be in good shape for the final exam, based on what I see. So yeah, so that's it. Okay, and let me just check the announcement. I think there's something else I remind of. Oh, so I did put the final for me. Okay, so I did put the final there. It's 4, 7, 10. Oh, so if you have not done the test already, test number 3, make sure that you do that. The deadline for that is the 4th. If you have any issue with reserving a date, let me know so that I can arrange for you to do it during my office hours. All right. Oh, so here are some other reminders. So I did talk about the final. Oh, yeah, I should say this. I should remind you about this. So again, because of the issues that we have been having with the testing centers, especially at Ocala, if you prefer to do the final here, then basically you can do it here, December 9th, as I said before. But you can do it at the testing center as well. but you have until the 11th to do it, right? Between December 8th and 11th, all right? So those are some options for you, because I know that, you know, some of you, especially those of you out there in Zoom, you may have some challenges coming here to do the test on that date. So you still have the option of doing it at the testing center, right? So those are the options for you guys, all right? And then finally, if you have any assignments that you have not turned in, you have until December 7th to turn it in. After that, I will not be accepting any late assignment, all right? Okay, I think that's it as far as announcements are concerned, all right? So that's it, folks. I'll be available for office hours, of course, so if you have any questions. So I guess the next time I'll see at least some of you will be next week for your final exam, all right? Well, that's it for today. All right, yeah, chapter 2 is up, okay. Because you didn't, up to you. Yes, sir.
I couldn't get a testing date for the test this week.
Oh, okay. Okay, can you come by my office today, upstairs? If not,
I work.
oh, yeah, work, okay. I'll be, okay, let me tell you where, let me tell you my situation. I'll be at Ocala campus tomorrow from 2 to 5. Thursday, I'll be here from 2 to 5. And Friday, I'll be at Ocala from 2 to 5. So,
I could work out Thursday.
okay, so, all right. So this is what I want you to do. On Wednesday, shoot me an email, just remind me, so I can
Okay, and then show up here
upstairs. I'll need room 208.
to wait to eat.
Yeah,
Pretty much.
yeah. Yes, sir. All right? Mhm. Okay,
What's the answer to number 5, RE, because the last question is simply about.
because they all have the same number of electrons in the outer shell, in the.
Okay.
In the valence shell. Okay, oh, some questions. Man, I'm missing the question that you guys are asking on your Zoom. I apologize. Okay, so, let me see here. Since we're not doing chapters 12 through 15. We'll. Hold on. Okay, I don't understand your question.
She's saying because like in class we only covered chapters 1 through 11, but we didn't cover chapters 12 through 15. So like she's wondering if chapters 12 through 15 is going to be on the final.
Okay, so I said, yeah, 12, will be on there. But 50 will not be, 14 and 50 will not be, because we just haven't got those, right? So basically, the final exam would be basically everything from chapter 1 through chapter 13. Because remember, we went to chapter 10, then we skipped to 13. And then we did 11, and I'm saying that 12, you have the option to do. I know, she's asking, is assignment 12 extra credit? Not really, but it's up to you if you want to do it. If you don't do it, that will just be seen as a drop score, because remember, I'm dropping the lowest 3 assignments. All right? So I hope that answers your question. Okay, so for you guys out there in Zoom, that's it. I'm going to sign off now, all right? So